Question 27 relies upon us recalling that the force between two charges is proportional to 1 over their separation squared. If we triple their separation, that means 3 squared, so that becomes a ninth of the force. So the answer is D. In question 28, it tells us that there's a point on this line where the potential is 0 volts. That means the potential from P and the potential from Q must be equal and opposite to one another. It wants us to find the distance from P, so we'll call this distance R, and we're going to use V equals Q over 4 pi epsilon naught R, which is the formula for potential. What we can do is just equate the potential from P and the potential from Q. So 4 microcoulombs over 4 pi epsilon naught R must be equal and opposite to 6 microcoulombs over 4 pi epsilon naught. In this case, 100 minus R is that distance. Notice I haven't bothered converting my charges because they're going to cancel straight away, as are my 4 pi epsilon naughts. And I've kept my 100 in millimeters here because that will give me an answer in millimeters too. If I cross multiply, I end up with 400 minus 4R is equal to 6R. So that R comes up here. So I end up with 400 is equal to 10R. So R must be equal to 40, and so the answer is A. In question 29, we're comparing electric and magnetic fields. When a charged particle enters an electric field, it behaves a little bit like a mass under projectile motion. In other words, we end up with parabolic movement motion, so it's either C or D for the electric field. In a magnetic field, the motion is circular, so the correct answer must be C. For question 30, part A, all we're doing is completing with units and whether they're scalars or vectors. So the unit of gravitational potential is joules per kilogram, and because it is a form of energy, it's a scalar. Electric field strength, newtons per coulomb. Fields have to have directions, so it must be a vector. You should write the full word when completing it under exam conditions. Magnetic flux density is measured in Teslas. Because magnetic flux density, the direction is important, this is also a vector quantity. Magnetic flux, on the other hand, is a scalar. In this question, we need to imagine a situation where a particle with some mass, which must be acting vertically downwards, is suspended by an electric field, which must act in the opposite direction to the weight which acts downwards. So here we can say that the upwards force, which must be equal to EQ, must be equal to the weight, which is mg. So we're after calculating E, so E times the charge, which is 3.2 times 10 to the minus 12 coulombs, must be equal to the mass of the particle, 4.3 times 10 to the minus 9, times G, 9.81. If we rearrange that, we get E being 13,200 newtons per coulomb. That's to 3 significant figures. Really, we should give that answer as just 13,000 newtons per coulomb. If the field acts upwards, so the electric field is acting this way, state the sign of the charge carried by the particle. Well, the force is upwards and the electric field is upwards, and the electric field gives us the direction of a positive charge, so the particle must be positive.